video report on oscillations. In this lab, I analyzed the motion of a spring mass system using tracker software and a computational model in GlowScript. I'll explain how I modeled the motion, compared my experimental and simulated data, and discussed whether the energy principle was satisfied. Okay. The purpose of this lab was to investigate oscillatory motion and analyze how energy changes over time in a spring mass system. We wanted to see if the energy principle holds true, meaning the total energy remains constant even as kinetic and potential energies exchange. We also estimated the oscillation period using X and Y position data. Here you can see a picture. In this experiment, we used the energy principle and Hooke's law. Hooke's law states that the spring force is equal to negative K times the displacement from equilibrium. The energy principle says that changes in a system's total energy must equal the work done by external forces. In this closed system, total energy should stay nearly constant through kinetic, gravitational, and spring potential energies during oscillation. So, a tracker experiment and data collection. Here you can see the graphs. Motion was tracked using tracker video analysis. We extracted the X and Y position versus time, then we calculated velocities and total energy from position data. And we compared the measured motion to the simulated model. Okay. In GlowScript, I built a model of the same spring mass system. I imported my tracker data and used Newton's second law to update the velocity and position at each time step. Spring force and gravitational constant were calculated using the same constants as in the physical setup. The simulation then plotted both predicted and observed positions over time. So these are my plots of energy changes over time. As the mass oscillates, kinetic energy and spring potential energy trade off while total energy remains nearly constant. Gravitational potential energy oscillates slightly due to the vertical component of motion. Small variations in total energy likely come from air resistance or calibration error. So I estimated the oscillation period using both X and Y position data. From the X position graph, the period was about what you can see here, and from the Y position graph, the period was about 0.87 seconds. These two are close, confirming consistent oscillatory behavior in both directions. What does it mean? Some differences between the experimental and simulated results likely come from several sources of error. These include minor inaccuracies in calibration, difficulty tracking the center of mass, and neglecting air resistance or damping in the model. The energy principle confirmed that our model correctly captures real physics. Our oscillation period agreement shows that tracker and GlowScript align. Small differences highlight limitations of experimental precision, and they also demonstrate that conservation laws can verify the accuracy of models. So our uncertainties came from tracker calibration, slight tilt, friction or air resistance was also not modeled, and just little things between the simulations. So in conclusion, the energy principle was satisfied in my system. Total energy remained nearly constant over time. The X and Y period estimates were close, verifying constant oscillations, and this experiment demonstrated that computational modeling is a powerful way to visualize and verify the physics of real-world motion.